I'm going to go through, this is part 2, the chapter 28-29 lecture, and try to do some examples. I've usually done these on a blackboard. I may end up doing that at some point, but I want to get these across to you at the same time, and it is kind of hard for me to go into school at this point. So there's going to be kind of a lot here, but nonetheless, I think it'll be helpful. So uh, there's an example here, there's an example on the next page, and then there's a final example that I'll do. So I want you to think about finding potential and potential energy using point charges. I'm going to ask some questions along here with some different examples, and I'm going to end up waiting, pausing at times so you can think to yourself and answer those questions. So I'll tell you when I think it would be good to pause. So I want you to think here that for this example, we've got a fixed positive charge and then a test charge over here. Sometimes this is called a probe charge. So this is the source charge. It's much larger than this. A test charge is 0. So I want you to think about the fact that if this test charge is way far away at infinity, there's no interaction between it and the fixed charge. So therefore, if there's no interaction with it, what I would say is there's no potential energy at that particular point. So in this particular case then, that also means if this is the fixed charge, then at an infinite distance away there would be 0 electric potential as well. Now if we move this from really far away, let's say I'm down here, and moving it close to the fixed charge, essentially, if I get close, the potential is positive. Why? Because this fixed charge is a positive charge. It would have positive voltage, and in fact, it would end up being something where the lines get closer and closer together, the equipotential lines, as we get closer and closer and closer. So it's like a mountain peak. So potential is positive, KQ over R. It would also take me work to do this. So if I was pushing a positive charge up here really close, I would need to push on it. And in fact, when I push up here, that total force times distance means that I would add energy to it. So if I do this, I could think of the amount of potential energy I add is equal to Q times that change in potential. It would also be equal to force times the distance. But the force is changing because, as you can imagine, as I get closer and closer and closer to this positive charge, it takes more and more force to push this test charge close. So the easier way to think about the change in potential energy is Q times delta V. So find the change in voltage. If this charge doubled in magnitude and I started an infinite distance away, there would still be no electric potential and no potential energy. If I move this double charge now, so actually I will do this, I'll call it plus plus. Oh, I'm not going to italicize it. If I call it plus plus, and I move both those charges close up here, it would take twice as much force at any particular point, oh my goodness, to cause them to move closer. So I would have to do twice the work. So when we think about the idea that electric potential energy is Q times delta V, the delta V that this increases as you bring it from far away is still the same amount, but the charge is twice as much. So it would take more work to do that, and I would increase by double the amount of electric potential energy if I move 2 charges from an infinite distance away to very close. Okay. Now, I want you to think about if we have the same idea of the same fixed charge, but a negative test charge. Once again, at infinity, we see that the potential is 0. Why? Because we're an infinite distance away from this. And the potential energy is also 0. Near the positive charge, the potential is still positive. Now you might say, well, why is that? Well, because the potential is caused by this charge, the source charge. So whether there or not there are other positive or negative charges around, the electric potential in space is caused by this fixed charge. And again, we're assuming these test charges are very small. So if I bring this negative charge, it ends up getting to an area of higher potential. That's true. But it ends up getting to an area of negative potential energy. Well, let's think about why that is. So now if I have something like this, say I have a negative charge here, and I start really far away, I don't have to push this to get close to the negative charge. If I just tap it a tiny little bit, doop, inside an infinite distance away, there's going to be an attractive force between this positive charge and this negative, which means it would naturally accelerate this and bring it toward itself. That means that the kinetic energy is going to increase. Well, if kinetic energy increases, that means my potential energy would have to decrease. So if we can define an infinite distance away as the electric potential energy is 0 because there's no interactions with this charge and this charge at infinity, as it gets closer and closer and the kinetic energy gets more and more as they're attracted more and more, then we're going to end up having more kinetic energy. And due to the law of conservation of energy, we obviously have to have a loss of something else, and that's electric potential energy. The other way you could think about this is if I have this starting very far away, close to infinity, and I want it to approach close to this positive charge, but not to accelerate, think about what direction would I have to push on this negative charge in order for it to move close to the positive charge, but not to accelerate. Well, in this particular case, what I'd have to do is I'd have to have an arrow. I'd have to have an arrow pointing opposite that. In other words, my push would need to be against this negative charge as it moves closer. So if we think about work as being a change of energy, the work here, this force is directed exactly opposite the direction of this charge's motion if it were allowing it to come close to this. So essentially, that would be negative work, which means we'd have a negative change in potential energy. Kind of weird. So now, if we have this negative test charge doubles in magnitude, so it's very far away but negative, so 2 negatives instead of 2 positives, we start very far away from this, then we still would have 0 electric potential out here, 0 electric potential energy if we're at an infinite distance away. But now if we bring it closer and closer and closer, we're going to gain more kinetic energy. We're going to lose electric potential energy. So the electric potential energy gets more and more negative as we get closer. So it gets twice as negative. Why? Because double the force is acting on it. And the force is attractive, which means to keep this thing accelerating, we'd have to have a push against its change in motion. So now we're going to go here to other examples with uniform electric fields. So we're going to use parallel plate capacitors for this and point charges to differentiate between electric potential and electric potential energy. So remember, this is our formula for electric field strength. Negative dV over dx. This should be dx down here. Maybe I'll do that. And I want to make it black and not purple. Don't need to bold it. Oh no, that's voltage over distance, duh. So this is, now I'm replacing the variable distance with x. Never mind. Okay, so here, let's say I've got positive 200 volts and 0 volts. So this would have a bunch of positive charges on it. This would be neutral. So the way you can tell that electric field is pointing opposite the direction is here we have a positive potential on the right side and 0 potential on the left side, but the field is pointing from right to left. So that electric field is pointing in the negative direction here. What's its strength? Well, it's 200 volts divided by 2 meters. So that's 100 volts per meter, or 100 newtons per coulomb. So now if we placed this plus 1 coulomb charge in the center, the higher potential or the higher voltage would be on the right-hand side. Okay. So over here. And where would the charge have higher potential energy? Also here on the right-hand side. In other words, if I start this in the middle and I want to get it over here, I'm going to have to push it over there. Pushing in the direction of motion, that would increase its electric potential energy. So you probably could define this as having 0 electric potential energy over here. So it would have higher kinetic energy on the left side. In other words, if I let this thing go, it's going to zoom or accelerate to the left side, gaining kinetic energy as it goes, losing potential energy. So when the charge is in the middle, what's the electric potential? Well, here, this plate is 0 volts. By definition, here, this plate is 200 volts. So if I were to draw a line, I don't like the fact that it's purple still. I might make it black. So in the middle of this, halfway in between, this electric potential line is halfway between plus 200 and 0, so that's plus 100 for that equipotential line. Here I'd have one to be plus 150. Here I'd have one to be plus 50. So at this point it's plus 100 volts. What's its potential energy? Well, if I look at Q delta V, or Q times electric field strength times distance, with respect to this plate being 0 voltage, and might be my 0 side for potential energy, I could say that at this particular spot, this positive charge would have plus 100 joules. 1 coulomb times 100 newtons per coulomb times 1 meter of distance. While 1 meter, it's 1 meter from the middle to the left-hand side. Now, if we assumed a negative 1 coulomb charge here, and let's say that that negative 1 coulomb charge was 3/4 of the way to the right, which is over here, the right side still have higher potential because by definition it's at positive voltage. However, this thing would have higher potential energy on the left side, lower potential energy on the right side. Notice that that changed. Why is that? Well, because this thing is going to want to zoom off to the right side because a negative would be attracted to this positive area. So the negative charge would have the highest potential energy over here, the lowest potential energy over here. So at this location here, which is at plus 150 volts, the potential, again, here is plus 150 volts. It's 3/4 of the way to the right side. The energy, however, QED, charge, electric field strength, and distance it could travel, well, this thing can only travel over here half a meter if this is 2 meters wide. It's going to accelerate to the right and hit this plate after half a meter. Well, right now, that's negative 1 coulomb, constant electric field strength, negative 0.5 meters. So right now it has plus 50 joules of electric potential energy. If this were a positive charge at this location, it would zoom to the left side, so it would be plus 1 times 100 times 1.5 meters, and that is going to be a total of 150 joules of potential energy. So let's go over to this one now. So we have a bit different field strength here. This is plus 100 volts, negative 300 volts. There's 1 meter in between them. So, by the way, notice also we can find a particle's acceleration if we know its mass, charge, and field strength. So if we could know the charge on this, say it's 1 coulomb, and we know the field strength, we can figure out the net force. But to find the acceleration, we still need Newton's second law and to figure out mass. So I think I'm going to put that line back in there because I bet I'm going to need it. Anyhow, field lines here point to the right. So the change in potential is 400 volts from plus 100 to negative 300. In reality, on a normal capacitor, however much of this would be positive, this would be negative. So it'd be like plus 200 on this side, negative 200 on this side. I wanted to show this as asymmetric only to show you that to figure out the field strength, all we're interested in is change in potential divided by distance. So now if we had a plus 1 coulomb charge placed here in the middle, that's half a meter from the left side, half a meter from the right side. Which side is a higher potential? This side is the higher potential. It doesn't matter whether the charge itself is positive or negative. What matters is this area is at a higher voltage, so by definition it's at a higher potential. Where would this charge experience higher potential energy? Over on the left side. Why? Because I have to push it to the left side. Whereas if I let it go, it's going to automatically accelerate to the right side. So it would have greater kinetic energy on the right side. When in the middle, so that's this, what's its electric potential? Well, I've got plus 100 over here, negative 300 over here. This middle spot would be negative 100 volts. So it's like it's below sea level at this point. If we go back to the gravitational analogy. The potential energy here, well, this thing it would end up accelerating over to this side, to the right. It's half a meter away from that. It's got 1 coulomb of charge. The field strength is 400 newtons per coulomb. So I end up with 200 joules of potential energy. Now, what would happen if we had negative 1 coulomb of charge 3/4 of the way to this side? Well, now, this thing has a lot of potential energy because it's a negative close to a negative voltage. It's going to want to accelerate to the left. So the left side here is still at higher potential because it's more positive. That isn't affected by these charges at all. The higher potential energy, though, and the higher kinetic energy are affected by the type of charge. So this thing's going to zoom off to the left. It's going to have higher kinetic energy on the left side, higher potential energy on the right side. At this location, 3/4 of the way to the right, this equipotential line would be at negative 200 volts. Finally, its potential energy would be plus 300 joules at this side. Why? Because if I go QED, this is going to be Q of negative 1 coulomb. The electric field strength is 400 newtons per coulomb pointing to the right. It's going to move negative 0.75 meters. Negative times negative is positive. That's a positive 300 joules. Now technically over here, this thing, I think I screwed up with how I did this. Technically, this electric field is pointing negative, and the distance that you would go over here would be positive. So I think I'm going to redo that. I think I'm going to say that this is going to be negative 1 times negative 100 newtons per coulomb times positive 0.5 meters. And I'm going to make that in red. And I'm going to bold it, I'll italicize it, and I'm going to make sure the background is sort of the same color. Oh my God, that's perfect. Wow. Who knew that I could fudge stuff like this? I'm a freaking genius. Okay. I like making up for my earlier mistakes. So something like that. Cool. The last part of this is the sample problem at the end here. Assume we have a Van de Graaff generator of 200,000 volts. It has a 10 centimeter radius. Find the electric field at 5, 10, and 20 centimeters from the center. B, the voltage at 5, 10, 20 centimeters from the center. Draw an electric field versus radius graph and a voltage or potential versus radius graph. So for part A, the electric field is 0 newtons per coulomb at 5 centimeters because it's inside a conductor. At 10 centimeters or 0.1 meter, I can get the electric field strength by using this formula we've had before, 2 times 10 to the 6th newtons per coulomb. At 20 centimeters, kq over r squared again, 5 times 10 to the 5th newtons per coulomb. So that's decreasing exponentially. I get twice as far away from the surface, I get 1/4 of the field strength. For B, at 5 centimeters, it would be 200,000 volts, and at 10 centimeters. Why? Because it said this thing is charged up to 200,000 volts, and anywhere inside that, you would also have to have the same potential. Why? Well, in this case, if we didn't have the same potential everywhere inside the conductor, that means we have changing potential, which means we would have an electric field. So here, anywhere 10 centimeters or inside has to be the same potential. So I'm going to use, to find the charge on this, kq over r. So that lets me know how much charge is on this, by the way, 2.2 times 10 to the negative 6 coulombs. And I can use that now to find the electric potential at 0.2 meters away. I also could figure out, probably proportionally, that if at 10 centimeters I'm 200,000 volts, and I know this is inverse relationship, at 20 centimeters I'd be 100,000 volts. When I look at this, drawing these graphs, here the electric field is 0 inside, inverse square graph here as I get further away. Here, electric field positive 200,000 volts inside, inverse, not inverse square, but inverse graph here. So since electric field is rate of change of potential with respect to distance, since this is not changing potential, that is why it is 0 electric field. So once again, I hope that's useful and that it makes sense. Screencast, because I forgot to use code words for that. So the code word for this is pineapple, no, Hawaiian pizza. Hawaiian pizza. That's all. That's a code word. That's because Charlie and Tanner work at Donato's. So that's it.